recall a little bit what we are going to do at this point. We have completed some kind of solutions, right? Method 1, method 2. Method 1, iterative algorithm. Method 2, recursive algorithm by dynamic programming. Yeah, so that's what we did last time. But last time we also mentioned one possible way to find the solution. So that is find a math formula for Fibonacci numbers. Yeah, you can imagine if we find a math formula for Fibonacci numbers, we can plug in. Yeah, you can imagine f sub n equals, for example, some function f of n. Yeah, here we, let me just use the lowercase m. When you are given an input number m, you just plug it into that formula and do some calculation, then you find the answer immediately. That is the best thing we can have, right? The best thing we can have. All right, yep, okay. But the problem for the formula way, can you do it? Is it possible to find a formula? That's the main problem. For most computing problems, the chance to find a math formula for the solution is very small. Okay, yeah, so that's the fact we have, based on statistics. People notice this fact. Yeah. Only some small percentage case, then a formula can be found. Yeah. Fortunately, here we have that situation. Yeah. Fibonacci numbers, the recurrence relation, so simple, so beautiful. Then, mathematician, they develop some systematic way to find a solution. Not by guess and verify. Guess and verify, although it is a very useful strategy, but many times, how can you make a good guess, right? That part is hard. If you find a way to make a good guess, then that strategy is perfect. But the harder part is nobody is that smart. You can find a super close guess to the true solution. All right. Anyway, so here we have the situation, okay? Math formula. So the remaining of this module, let us spend our time on learning how to find math formula for Fibonacci numbers. Yeah. All right. When we start, we need to start with something very interesting, golden ratio. This concept, many of you at least heard of that, right? Golden ratio. Yeah. But it relates to Fibonacci numbers. Yeah. Look at this figure here. Yeah. We know the Fibonacci number F0, it is 0, F1, it is 1, F2 also 1, sum of the previous two numbers, and a 2, 3, 5, 8, and so on. All right. Then the 0, the first one, yeah, because 0 means nothing, right? So we drop it. Then we use 1 to make a square with the side length 1. So that's the F1. F2 also 1. So we place here F1, F2, right? Then F3, yeah, square with side length 3, 2, we arrange in this kind of, fitting way. Yeah. Then F4, F5, and F6 here. You can see the length of these squares fits in a perfect way. Yeah. And another interesting property is if we draw arc in this way, with the center at one of the 4 vertices of the square with radius, the side of the square, and then draw the quarter arc, this quarter arc, okay, for each square, and try to arrange them in a natural way. So at the end, we get this, nice spiral curve. How about that? Yeah, so that's something very interesting. Yeah. And some people even related to the painting, Mona Lisa painting, yeah, in this way. Look at that. Yeah. All right. So I read a book. Once I borrowed a book from the library, a small booklet, not very thick. The whole book is about golden ratio. So all different kinds of beautiful figures created, related to the golden ratio, that number. Yeah. Here, we are interested in the formula for Fibonacci numbers. Then that formula is related to the golden ratio. So that's the reason when we start, we like to start with the golden ratio definition first. All right. Here, this figure gives us the definition of the golden ratio. Yeah. Here, let me repeat it. Yeah. Let me use my own diagram to repeat the definition of the golden ratio. All right. Okay. So when we start, we we start with one like segment. Then we break it in somewhere in the middle, 2 line segments. Yeah. So we divide it into 2 line segments, one longer, one shorter. The longer one we use A, and the shorter one we use B. Okay. Then we like to have the ratio of these line segments satisfy the following condition, the ratio condition. A over B, that ratio, the longer over the shorter one, equals the length of the whole line segment, A plus B, over the longer one, A. All right. Yes. Following this kind of, we can call it some natural rule, right? Yeah. Some natural, because ancient people, yeah, I don't know who is the first one discover this relationship. Yeah, yeah, it must be some ancient, guy. Yeah. All right. So with this relationship, let us simplify a little bit, because A over A, that is 1, then B over A. Yeah, 1 plus B over A. the shorter one over the longer one. All right. Now we want to find some, more explicit racial number. So here in this equation, we cannot see explicit racial number. What's that? We just see A and B. We do not know what is the ratio of A over B. All right. Yeah. So here, even after this simplification, look at that, this part. Even after this simplification, we have two variables, right? A and B, two variables. Yeah. If we skip the middle one, we have one equation with two variables. Can you solve that equation? As we know, in order to solve some equation, or in order to solve some system of equations, yeah, so based on our experience or some observation, people need to have this kind of relationship. Yeah. The number of equations in the system should be the same as the number of variables. Then you have a chance to solve that system. Here, our system has only one equation, but two variables. Based on that kind of our background, it's not sufficient to solve this equation. But fortunately, from the figure here, the length of A and the length of B actually is not really important. The important part is the ratio of A over B. Okay? The ratio is important. The specific length is not quite important. For example, you can double A length and at the same time also double B length. Then you have the same ratio, right? So we do not need to really find the length of A and the length of B. We only need to find their ratio. In that situation, we do not need to completely solve that, the given equation. Yeah. We just focus on the ratio part. Yeah. So with that understanding, now we modify our goal a little bit. Yeah. This time, because the ratio of A over B, that is our main focus. How about we just introduce a new variable for it? X equals A over B. Yeah. So we don't care how much is A, how much is B. We really care about the value of A over B. So let us make that value, the ratio value, a new variable X. In that way, two variables are replaced by one new variable. How about that? Two variables A and B, after we make that substitution, our new equation only has one single variable, X. How about that? Okay, so that's a, nice improvement. Yeah. With that substitution, this time, that B of A is just a 1 over X, reciprocal of X. Yeah. So in order to represent B over A, we do not need to use new variable, right? We can use the old variable X to represent it. That is 1 over X. Now our new equation becomes X equals 1 plus 1 over X. This time, our previous rule related to equation solution is satisfied. One equation with one variable. Then we have a pretty good chance to find the solution of this equation. So in my next slide, let us find the solution of this simplified equation. Yeah. All right. Yeah, so let us remove the denominator. We have this x squared equals x plus 1. So that is a quadratic equation. Yeah. So we need to solve this quadratic equation. And we know there is a quadratic formula we can use. Right? Yeah. So let us look at this quadratic formula. Yeah. For the standard quadratic equation, a squared plus bx plus c equals 0, but a must be non-zero. Otherwise, it won't be a quadratic equation. It will be a linear equation. Yeah. Then the formula is this. Yeah. All right. Numerator negative b plus or minus, two possible solutions. Root of b squared minus 4ac and a denominator 2a. Yeah. I believe everyone, at least, you may not be able to memorize it exactly, but at least you have some experience using this formula. Yeah. Here, let us plug in, because we have that ABC coefficients. A is 1, the square coefficient. B is -1, and C, the constant term, also -1. Let us just plug into our quadratic formula, and after a little simplification, we have this 1 plus minus root 5 over 2. Two possible solutions. The first one, 1 plus root 5 over 2, but the second one is 1 minus. Yeah. But here, the approximate value is 1.618. Yeah. But why we drop the -1? Yeah, the reason is simple. 1 minus root 5, that is a negative number. Remember, what is the geometric meaning of x? The geometric meaning of x, that is the ratio of a over b, right? Line segment. A over b, we know by the geometry, it should be a positive number. So that's the reason we drop the negative value here. Yeah. The golden ratio cannot be negative, right? So it makes sense. Yeah. So we take the positive solution of this quadratic equation and find this, special number. This special number is not an integer, okay? And it is not a rational number. Rational number, right? Yeah. So the digits after, you know the definition of a rational number. Yeah. All right. So here it is an irrational number. Right? An irrational number. Yeah. At old times, people don't like the irrational numbers. Yeah. So if we go back to the Pythagorean time, at that time, people, Pythagorean, so they have a club. In the club, they believe everything in the universe, if you want to use some quantity to represent, you can use some integer over integer to represent any number quantities. That's the Pythagorean, club. So they believe that. They cannot prove that. They just believe it because they thought that must be the law from the God. Okay, yeah. This representation means a rational number. okay? Rational number. Any rational number can be represented as a fraction like that. M and M are both integers, okay? Yeah, integers. Yeah, but here, this golden ratio, it's not a rational number. Yeah, yeah, yeah. So that's something interesting. Yeah, people accept irrational numbers. It took a long time. It took a long time. People realized, wow, the irrational numbers also important in the universe. Yeah. Anyway, so here we derive this so-called golden ratio number formula here, but we don't like to write the whole expression 1 plus root 5 over 2 all the time, right? Because it takes some time to write it, right? Not fast. So people later, they use some Greek alphabet symbol phi to represent this special number. We have similar experience using pi, right? Yeah. Right? Is familiar with this pi meaning, okay? Yeah. But here we have a similar situation using phi to represent golden ratio. All right, yeah, okay. Then the magic formula for Fibonacci numbers, okay, yeah, yeah. We will see this is the magic formula. F sub n equals 1 over root 5 times parenthesis phi to the nth minus -1 to the nth over phi to the nth. Yeah, that is the Fibonacci number formula. All right, so here, this formula is quite unusual because in order to understand this formula, people usually, based on their intuition to understand it. Because by intuition, we know the Fibonacci numbers are integers. All right, integers. So we expect to have some integer expressions. But here, we do not have a straightforward integer expression. Now, what do we have here? The golden ratio, first term, phi to the nth, and the golden ratio also used in the second term. After that, we need to multiply another irrational numbers, 1 over root 5. After that kind of complicated computing process, we end up with some nice, beautiful integer. How about that? We go through operations with irrational numbers, a sequence of irrational numbers, but we end up with perfect integers. How about that? So that's something like magic. Okay, yeah, yeah. All right. Next, we like to understand this formula in 2 different steps. Okay, 2 different steps. Yeah. First, how do you know this formula is correct? Right? Someone told you this is the formula. Okay, but you still, before verification, you do not feel comfortable. Okay, so you want to check it, verify it, if it is correct. So the first step we like to do verification. All right, yeah. Then after verification, then we feel it's correct. We have verified it. Yeah. So we can use it without any question. Yeah. But after that, then you may have the second question. How do you find it, right? How do you find it? Yeah. Because to do verification, you skip that discovering step, right? You rely on some other smart people to discover this magic formula for you. But you like to know how to discover it. Okay, so our second step, derivation. We really want to know what is the systematic solution to find this formula. Okay, yeah. All right, so that's our remaining plan. Yeah. All right, so let me stop the the part. Yeah. All right. So I already explained. Yeah. All right. I already explained that. All right. Okay. Yeah. So let me stop right here and skip to jump to part D at this point. Yeah. The title, Fibonacci formula and linear recurrence relation. You can see in these two topics, we will do those two steps, verification step. So Fibonacci formula, this first topic corresponds to verification step. And the second topic, linear recurrence relations, this topic would provide us the systematic solution for that derivation part. All right, let's start. D.1, verify Fibonacci formula special cases. Yeah. Even for verification, that is not easy. We need to split it into two steps. Okay, the first step, we only work on special cases, smaller, simple, special cases. Then step two, then work on the general case. Okay. All right. Yeah. Let's start special cases first. Yeah. Our goal, how to show that this Fibonacci formula, yeah, phi, golden ratio number, yeah, it is true. Yeah. So for the verification, step one, yeah, we plug in n number starting with 0, the easiest case. That's trivial, right? You plug in phi to the 0, that's 1. Okay, yeah, phi, yeah. Denominator here also 1. You can see 1 minus 1, 0. Yeah. So this verification is trivial. All right. When we increase the number n, you will see the verification becomes harder and harder. Okay. Step two, this time we plug in 1 in our formula. Not too hard this time, so let us plug in the golden ratio number, becomes this expression, okay? But we feel the denominator 1 plus root 5, not very convenient to manipulate. So we like to convert it to an equivalent expression. I think you are familiar with the technique, all right? By multiply the conjugate, yeah. So here the conjugate root 5 minus 1, you multiply this number, both numerator and denominator, and you can do that conversion. Yeah. Then after that, then do some simple algebra, you will get the number 1. Yeah. Harder than the first case, yeah, but we can still handle it. Yeah. Case 3, this time plugging 2. Now you will see the expression becomes pretty complicated. Yeah. This time you need to take square of the golden ratio. Okay. Yeah. But if we are very patient, we can still handle it. Okay. Yeah. So the first square, we can apply the square formula, right? Square of sum, a plus b, square that formula. So we can get, the first fraction here. Yeah. The second fraction, a minus b squared, we can find the second fraction. Then do some cancellation, simplification. At the end, we get this 1. Yeah, so we verified the first 3 simple cases, 1, 2, 3. How about that? That's the first step. Okay? 3 simplest cases. All right. Yeah. Next. Now it becomes harder and harder. What should be the next step? It's not enough only verify the first 3 cases. We need to verify all the cases, right? Yeah. For all the cases, some of you may relate it to mathematical induction. Mathematical induction. Natural way to do it, because nobody can verify all the cases. There are infinite many cases, and it's not necessary to do that. Yeah. Mathematical induction solves that problem. If we apply mathematical induction, we just do some limited work, we can verify all the cases. That's the power of mathematical induction. Okay. Yeah. All right. Before I go to the mathematical induction, this time I won't skip it. Yeah. Last time I skipped it. Last time when we solved that binary bit problem, I skipped the mathematical induction step. Yeah. Yeah. But this time I want to show you the power of mathematical induction. Yeah, at least you get some idea how to use mathematical induction another time. Yeah. All right. But before we go there, I like to do another verification, because here I like to introduce another technique, different from what I used in the previous slide. Previous slide, I just used the, straightforward computation. But here, that's too complicated. It's not realistic. Continue to use that kind of straightforward computation. All right. So here, for case number 4, when n equals 3, in order to find its value, I like to use some smart way to do it. Smart way. Avoid complex computation. But in order to avoid that, you really need to use some special properties for the golden ratio. Yeah. All right. Here, degree 3, although it's not a big number, but for our computation, regarding our computation, it is still too high. Yeah. You raise the golden ratio number to cube. How much computation work you need to do? Think about that. A little scary, right? Yes. Most of you, I believe most of you feel a little scary here. Yeah. So we need to find an alternative way to avoid that kind of messy computation. Okay. All right. Now the question, how to reduce the degree of phi cube? Yeah. This question. Yeah. We need to apply some properties for the golden ratio. Golden ratio is a special number. It should have some special properties. Yeah. So what are those properties? We need to find those properties first. Then we can take advantage of those properties and simplify our representation as much as we can. Yeah. All right, so here, 2 properties. The first property, 1 equals phi squared minus phi, the first property. The second property, phi squared equals phi plus 1. If you use the golden ratio in your algebra calculation, you can use these 2 properties anywhere you like. Yeah. But why? How to get these 2 properties, right? You may wonder how to derive these 2 properties. Very simple. We go back to the starting point. We know phi is a root of this quadratic equation because we solve this quadratic equation to find the golden ratio expression. So if we plug in the golden ratio into this quadratic equation, we should get an equality. Phi squared minus phi minus 1 equals 0. Okay. Can you see from this equality, we can just change the expression, move this term to the other side, we get a first equality, property, right? Then move these 2 terms from left to right, then we get a second property. Okay, so that's simple. Just you can see these 2 properties, just 2 different ways to write the original identity for the golden ratio. Okay, yeah, nothing new. Yeah, but these 2 properties, very convenient in our calculation. So let me show you how to do that calculation. Yeah. So I need space. The remaining little space, I need to complete the verification here. Yeah. All right. So let me start simplification. Phi cube. Yeah. When you see phi cube, can we break it into phi times phi squared? Right? Yeah. The reason is we want to single out that phi squared part. Yeah. Because after you single out that phi squared part, you can apply the second property. Okay, so we can plug in, there's a second property. We write it as phi times parenthesis phi plus 1. Okay, yeah. So then let us multiply through. So we get phi squared plus phi. Here you have another phi squared term, right? You can replace phi squared by phi plus 1 the second time. Yeah. So after that, you get this 2 phi plus 1 representation for phi cube. Yeah, so that's the first part. Then the second part, the reciprocal, 1 over phi cube. Yeah. This one will be a little harder because phi cube is at the denominator. Yeah. The manipulation will be more tricky. Okay, yeah. So let's try. All right. First, we notice the denominator is 1. Can we apply property 1 for the golden ratio? Replace 1 by phi squared minus phi. Okay, because we see that 1, yeah, so we do this kind of substitution. The reason is we can have some cancellation in this way, right? The numerator, denominator, they have a common factor phi. We can do cancellation. Yeah. All right. After cancellation, now we have phi minus 1, numerator, denominator, phi squared. Yeah. How to do next? The next step, because there are several probabilities, right? One is you see the denominator phi squared. If you replace phi squared by phi plus 1, that won't be good, because in order to do cancellation, if we keep the phi squared term at the denominator, it will be easier for cancellation, right? If you switch to phi plus 1, it becomes harder to do cancellation, right? Yeah. So that's the reason we don't replace numerator phi squared by phi plus 1. But we notice there is 1. 1 appears in a numerator. When you see 1, you can connect to the first property. 1 equals phi squared minus phi. So we apply the first property another time. After simplification, we have this 2 phi minus phi squared. Okay? That means with this new expression, we can do further simplification, cancellation. Another phi could be canceled out. Okay? Yeah. After cancellation, we have this 2 over phi minus 1. Yeah. Much simpler. Yeah. Because the denominator now becomes phi. It's now phi cube. The old denominator phi cube, the new denominator just phi. All right? Yeah. Now let us add up these two terms, two expressions. After simplification, we have this 2 times phi plus 1 over phi. This relationship. Okay? This relationship we can recover to the original relation for Fibonacci numbers that equivalent to phi 3 equals 2 phi 1, right? Yeah, if you look at the original formula, you have this equality to be verified, and we know that's true, right? Yep, that's correct. Phi 3 equals, 2f1. Yeah, let's say 2f1 equals 2. Yeah, so this, phi cube expression, we end up have this answer 2. So that's the case 4 verification. Okay, yeah. So here the reason. When we apply mathematical induction, we do not have to verify case 4. For mathematical induction, we only need to do first 2 cases, case 1, case 2. That's enough. Okay. The reason I did 2 extra cases, case 3 and case 4, I like to show you some computation techniques a little bit. Okay, because in your homework assignment, homework number 1, I will create it today, sometime today. You will do this kind of simplification. all right, you will have a chance to do in this way. Okay, so that's the reason I show you how to do it. All right, so let's continue on the next part. Oh, what's that? Yeah, yeah, because, but yeah, the title is wrong. You know, the title, yeah. D.3, you know, a general case. General case. All right, yeah. Okay. Now we are ready to verify the Fibonacci formula, mathematical induction this time. Yeah, yeah. I hope I complete this part before the end of this class. Yeah, I have a chance to complete it. Yeah. All right. Powerful tool. I already mentioned that mathematical induction. Yeah. I hope you still remember how to use mathematical induction. Yeah. But here I review a little bit. Yeah. First, we need to verify the base cases, right? Yeah. Check the base cases. Yeah. But for the base cases, how many base cases are sufficient for us to apply mathematical induction? Yeah. Look at this recurrence relation. Yeah. At the right-hand side, we have two terms. Two terms. When you have two terms, then you need to verify the first two base cases. If you have three terms, you need to verify the first three base cases, and so on. Okay, all right. So here, we need to verify the first two cases, F0 and F1, and we did it. Okay, so we go to the second step. That is the mathematical induction. Okay, yeah. Make assumption, sorry, not induction, assumption. Yeah. Before induction, yeah. Assumption. Induction assumption. All right. Yeah. So what is the induction assumption? Yeah. We write in this way. Yeah. Assume that the formula is true for 2 less than equal to k less than equal to n. Yeah. Here we are looking at the k place. K is in this range between 2 and n inclusive. That's the k range. Yeah. So we can write f sub k equals that, you know, the form of the Fibonacci formula, but our variable is k. Okay, yeah, that's the induction assumption here. All right, yeah, okay. Then step 3, we need to verify that f sub n plus 1 equals the same form, but with the variable part replaced by n plus 1. Okay, yeah. So here you can see yn plus 1, right? Yn plus 1, yeah. Here, k is in the range between 2 and n, that's the range, all right? In order to move this result further toward infinity, yeah, we move toward the infinity direction, okay? Yeah, so we move to the next one out of the range. Yeah, you need to try out of the range. If you still have the same formula, okay, then the one number that after this range, that is n plus 1. So in other words, you enlarge the range, okay? You enlarge the range. And eventually, you want to enlarge the range as far as infinity. How about that? How about math? Okay, that's the goal. All right, yeah, all right. But here, there is another thing I like to point out. Yes, because some of you, if you really pay attention to the induction assumption, especially this range part, you may notice that it is a little different from what you used to use the mathematical induction. Yeah. So here I like to explain a little bit why here we use this special range thing. Yeah. So when you go back to look at the mathematical induction, the theory part, you will see there are two versions, version 1 and version 2. Okay. The version 1 is a weaker version. The version 2 is a stronger version. Okay. So here we use the version 2. Okay. Yeah. Actually, both versions are equivalent. Although we say weaker, stronger, but actually we can prove they are essentially, they are equivalent. They are equivalent. Okay. They look slightly different, but they are essentially the same. We can prove that. Okay. Yeah. Yeah. So for the version 1 here, the version 1 is if I change, I can modify our version 2 to version 1 easily. So if I modify this range to version 1, I would like when k equals n, this is the version 1. Not the range, just the n. K equals n, it is true. That's the version 1. But version 2, we make that range larger, not just the n, it covering all the integers in this interval, closed interval, from 2 through n. It looks like you make more in your assumption, right? Make a more stronger in your assumption. Yeah, but actually it's equivalent. You can show, yeah, this version simpler, but we can, do one after another. Eventually we can show they are the same. So don't worry. Yeah. Yeah. The version 1, usually you use the version 1 to solve relatively simple problems. That's enough. You do not need to use the stronger assumption. The weaker one is quite sufficient already, enough. All right. So you don't need more powerful tool. All right. A stronger, weaker tool is already enough. Okay. That's the reason we have version 1. But for some harder problems, the weaker tool is not good enough. So we have to switch to a more powerful tool. So that is the version 2. So that's what we are doing here. All right. Yeah. Okay. Yeah. That's the background, some background about mathematical induction. Okay. Now let me move to the real tough work, the final punch of our verification work. Yeah. Not too much work, actually, pretty simple. Yeah. So let me start that step. Yeah. All right. Formula transformation. Yes. Here we need to do some exploration related to the formula form. Yes. All right. We know this is true, right? Yeah. Before the verification, so that is just it is given. So it is true. All right. Yeah. It is given. All right. Yeah. Now we want to manipulate this formula. Okay. Our starting point. Okay. All right. Then to write the Fn plus Fn minus 1, we can write in this form. Do you know why? Why we can write in this form? Remember our mathematical induction in the previous slide, our assumption, mathematical assumption, or induction assumption. In our previous slide, we say when K belongs to the closed interval of this one, we have that formula, right? That's our induction assumption. For the first term expression, we take K equal to N. That's in the interval, right? So we can use it. All right. The second one, we take K equals N minus 1. That's also in that interval, right? So we can also apply that induction assumption formula, right? So these two applications of that induction assumption formulas, both legal. Okay? Now here I just want to show, after we check the range, these two places for the application, it's legal. They are legal applications. So we can continue. Okay, all right. Then let us do some, algebra manipulation. Okay, so we put a phi to the n and a phi to the n minus 1, these two terms together, because they have the similar structure. Yeah, a power function, that's their similar structure. Also, we put a fractional expressions. They have also similar structures. The third and the fourth terms, those two terms together, they have the similar structures. So we put them together, okay? Because we want to explore their properties. Oh, yeah. All right. Now, remember, what is our goal? Okay, our goal, here, remember, so let me write one more step, because here I may jump too fast. Our goal, remember, we want to prove that Fm plus 1 equals this form. Right? That is our target. Our target. So compare our target and the current expressions when you compare, right? You can see both places, they have two parts. Yeah. All right. Integral part, right? Integral part, let me call it that way, integral part and the fractional part. Okay, so here also integral part and the fractional part, right? When you compare structures, they both have integral part and the fractional part. Can you automatically make the connections like this by the natural law? So here I may like to mention that some natural law, okay? So integral part should be the same and the fractional part of both sides should be the same, all right? Yeah, if you ask me why, because the structure, same structure, the part with same structure should be the same, all right? That's that kind of connection, yeah. Now here, we need to verify this. We want to show the integral part should be the same. Yeah. So here, to be verified, okay? to be verified. All right. Then after that, we also need to verify their corresponding fractional part also be the same. Okay, yeah. All right, so let's try. Yeah. Yeah, so integral part should be the same, fractional part should be the same. All right, yeah. So that's to do, our to-do work. Okay, yeah. We need to do something to show both equalities are true. Yeah, all right. To show the first equality, we start with our golden ratio property number 2, phi squared equals phi plus 1. Golden ratio property number 2, okay? After that, let us multiply phi to the n minus 1 power, both sides. After simplification, we get this expression. That's exactly our first integral part equality. How about that? So we get the first integral part equality verified. Yeah. Then remaining work, we work on the fractional part verification. Okay, all right. So let's, try. Yeah. All right. Yeah. Now, for the fractional part, in order to show it is true, yeah, so here we put a question mark because this equality is true or not. We don't know, right? Our goal is to verify this equality, but it's unknown at this point, right? So how to do the verification? Yeah. So here there is a common way for this situation. Yeah. So we use backward thinking. Backward thinking. Yeah, it's quite common in problem solving. The backward thinking is commonly used. Here, let us use that backward thinking. All right. By backward thinking, in order to show this equality is true, we only need to show this equality. The second equality is true because we just do the operation, we multiply phi to the n plus 1 power both sides, right? Common denominator. We just multiply the common denominator both sides. Multiply the common denominator phi to the n plus 1 both sides. Then you get a second equality. All right. Backward thinking, not done yet. Yeah. We'll keep going. Yeah. So the next step, this time multiply. Yeah, because there is a sign part. Still not quite right. We need to fix the sign part. So yeah, here covering a little bit. Multiply -1 to the n minus 1 power. Yeah, still we can see, yeah, the expression. Yeah. After that, that is 1 equals phi squared minus phi. How about that? Is this our first property? Yeah. So this one here, we use the second phi property. Here we use the first phi property. How about that? And we know this equality is true. It is just our first phi property, so it is true. Then backward thinking, the previous equality is true. Another backward thinking, previous equality is true. But this one is our destination, our goal, our target. And that means we verify the fractional part equality, and we combine with our integral part equality, so we get the, whole n+1 case verified. And by mathematical induction, we proved for all n greater or equal to 2. Here our verification is applied on n equal to 2. It is true. So we verify the whole formula. That's the whole process of mathematical induction-based verification. Okay? So we completed. I hope you can understand the details. So I went through a lot of things. I hope you can follow. Okay? All right. I run out of time already, 6:44. So let us stop right here, and I will work on your homework assignment number 1 soon. So you will see it quickly sometime today. All right, so that's it. Have a good evening.